Hi everyone. So today we will talk about all the interesting arithmetics, subtraction, addition with negative integers. And a lot of young students, especially in elementary schools, when they deal with the negative integers, they struggle when subtracting something in the parentheses, and inside that parentheses you have negative integer arithmetic. So it's very important to understand why some rules work. And let's quickly discuss what we learned last time. Last time we established some theorems and discussed the commutative law for addition over integers. So here's the number line, and the theorem that we studied says that if an integer m plus the negation of another integer, the result is the same as if m, the first integer, subtracting the second integer before the negation is taken. So m plus the negation of n equals to m minus n. And if the operation is not addition but subtraction, so m minus the negation of n, the result would be m plus n. Okay, very important concept. And we took pain to actually show this theorem is true. Then we talk about the commutative law. We do not provide a rigorous proof, but intuitively explain on the number line why m plus n equals to m plus n. Essentially, it's something like this. On the number line, you have a number m plus n. This can be considered as 0 plus m plus n, right? Because 0 plus any number equals to any number. You start from 0. Whether m is positive, where you will count forward, or m is negative, in that case you will count backward, meaning toward the left. It doesn't really matter. So m plus m equals to m. So when you have an integer m plus m, essentially it's the same thing as 0 plus m plus n. So in that case, we will see that the m and n, one will be, say, 0 plus m plus m. You will actually do two operations. One is generated by m, the other is generated by m. Either can be count forward or count backward, meaning count toward the right or count toward the left. The commutative law simply says that which one goes first doesn't really matter, which makes sense, right? If you need to say, if both are positive, then you will just have the regular commutative law. So we know m plus n equal to m plus m. If both are negative, so essentially it's a reflected version of the commutative law for the natural numbers, because in both cases you will count toward the left, and it doesn't matter you count which one first. The case becomes a little bit more interesting if one of them is positive and one of them is negative. So for the negative one, you will actually count downward, meaning that count toward the left, and for the positive one, you will count forward, count toward the right. But the commutative law really says that it doesn't matter which direction you go first. just think about you walking in two directions. One is the just opposite direction of the other, but in each direction you need to walk certain steps. So it doesn't matter which way you go first, as long as you do both. Okay, so that gives us some insight of how the next law works, which we know is the associative law for addition over integers. Here is important because we already know associative law for natural numbers. Now we want to generalize the same associative law from natural numbers to integers. And this is a little bit harder to understand because now integers could be negative, and unlike when we only had natural numbers, everything is positive, so we'll see how that worked. In that case, when all the three numbers were natural numbers, we were able to do some concatenation of line segments, right? We have three numbers, L plus M plus N. We actually grouped the last two, or the second and the third one first, to do that concatenation. But you'll see that it doesn't really matter which way you want to concatenate all the three. So if you concatenate the last two, then concatenate with the first one, you should still get the same total length for the combination of the three line segments. That's how we intuitively use the number line to explain why the associative law works. Now the numbers are integers, meaning that they could be negative. So how does this still work? Well, you can think about this. Just based on what we did with the commutative law, we'll think about the very first one, which is L plus M plus N, right? Without any parentheses. That's the natural order you will follow. But to emphasize the order, we put a parenthesis between the first two, and this one is not really necessary because the natural order of operations from the left to the right, that's default. But we can think about this. If without the parentheses, what does this expression mean? Meaning that starting at a number L, L could be here or somewhere here. It doesn't matter where it's located on the number line. Starting at this number L, let's just say it's here. L is here. We need to add two numbers, two integers. First M, then N. So we know when we do first M, it will be either count forward, meaning to the right, or if M is negative, we add the negative. That's essentially subtracting the positive, meaning that by the very definition of subtracting, we will count toward the left, count backward. But does it really matter? As long as you will have to perform this one, then this one, does it really matter you do which one first? It should not, because either of them just give you some counting, except that the direction could be opposite to each other. One is counting forward, meaning that you are adding a positive integer, or counting leftward, meaning adding a negative integer. So that gives us the idea that this should be, we can do this first, right? This should work, but this is not associative law. The associative law says that we want to prove L plus M plus N equals to, we group the last two first, not just changing their order for the addition operation. So this is not really associative law. But what can we do next? Well, now we know we have to do the first one first. At this very step, we can use the commutative law we just learned last time, right? We know this can be written as this. Right? This is just commutative law because we are only applying commutative law to the first two terms which are being added. Now, by the same logic, we can once again swap those two addition operation. That means that we can now move the plus m part forward. Okay, so this will be m plus L. So we can do this kind of money. We cannot directly group the last two as we wanted here, but we can gradually move the third one to the second one, then to the first one by either using this argument, where you have to do two operations. It doesn't matter which one you do first. Then we can, at some point, we use the commutative law directly to swap the order for the first two. So once we are here, what can we do now? Well, we can now use commutative law again to swap the first two. So this is really becomes m plus n plus L, right? So this step and this step are both directly using the commutative law, while this step and this step, we are using the argument that when you have two back-to-back addition operation, it doesn't matter which one goes first. That is just an intuitive explanation. But once we are here, something really interesting will happen, because by the very natural order, this is the same thing as this one, right? So we have to do m plus n first. And we understand it gives a number, an integer. Because with our expansion from natural numbers to integers, integer still is a so-called closed group. M plus n is integer. Now, we think about what can we do here. We can once again use the commutative law, because now we understand this will have to be evaluated first, which will give a number. So we can do this by using the commutative law again. And this step is once again commutative law. Look at what happened. This is exactly what we want to show the associative law. So this is a very interesting consecutive application of some result or reasonable argument that we have established for some seemingly more complicated situation. So this is the associative law for addition over integers with three arbitrary integers, any three integers, no constraint on the nature of those numbers. The associative law says that L plus M plus N, that's just the default order. You add those three numbers up. The parenthesis on the left-hand side is not really necessary, but only for the purpose of emphasizing this particular order. So put that into a parenthesis, but it's not necessary. The associative law is that L plus M plus N, we can group the last two numbers first and performing an addition between them. It's very important to understand that in the original expression, the second addition operation is not between m plus mn. The second addition here is between the result of L plus M and N. But now with the associative law, we can say we want to force an addition operation between the second and third first. I hope this cannot be emphasized enough. Otherwise, everything will become seemingly trivial. Why we are doing this in the first rule? Why associative law is important? What happens here is that without associative law, this particular operation has nothing to do the two operand m and n. This addition is between this result, which is L plus M first, and then with this one. So it's a operation between this result and the third integer m. Very important. It's not something between m and n at all. It cannot be thought as an operation between m and n. All right? But with the associative law, we force an operation between m and n first, and that happens to be addition itself. And then use the result as the input to the first addition operation for the same reason. So in other words, the first operation, addition operation in the original expression is only between L and M. It has nothing to do with anything involving M. But now, this operation is between L, which is still there, and the result of M plus N. So don't get confused. You have to remain crystal clear about every bit of detail of what you write as a mathematical matter. That's why it's important to understand this symbol, this subtraction symbol, has actually two meanings. One is a two operand operation, subtraction between two numbers. The other is a single operand operation, that's the negation. We use the same symbol for both, so that's why it could be horribly confusing. But as long as you keep a very clear mind toward the meaning of that symbol, you will not get lost. So here it's also important to understand what is this plus symbol. It's an operation between two entities, but you have to be very clear about which entity those two are. Okay? So the associative law really is important. It's nothing trivial at all. So when you have three numbers, add them in a natural order, L plus M plus N equals to L plus, you group the second and the third first. Okay, that's the associative law. And the way to explain it is we already used the commutative law, and using this argument, when you add two numbers back to back, it doesn't matter which one is being added first. Okay, that way we can move the second one into the first operation position, then use commutative law. Okay, so very intuitive, but you better understand why that's the case. So now we have generalized both commutative law and associative law from natural numbers, which are easier to understand. Now we generalize them to any integers, anywhere on the number line. Okay, so this is significant. By the way, it's important to understand that we only know integers. So a line, the number line here has infinitely many points, but it also has a densely distributed points. We are only looking at a very, very tiny fraction, not even a fraction, depending on what do you mean by fraction. It's just very small portion of the number line, because we have not discussed any other points between those any adjacent to integers, right? The vast of the number line have not been exploited by us yet. So we only look at those points which happen to be integers. When we learn fractions, we will learn many, many more points on the number line. That's just for the future. Now, remember, for natural numbers, once we have established commutative and associative law, they can be somehow mixed and used together, right? And for convenience, we came up with a theorem, just highly summarizing all kinds of situations where both the commutative law and the associative law are being used, and perhaps in a complicated way when you have the help of parentheses. Now we have a similar theorem for the same theme, but your customers now are not natural numbers, but integers. Okay, this theorem says that for any collection of integers, the last version was natural numbers. Now we have generalized numbers from natural numbers to integers. So for any collection of integers, adding them in any order result in the same sum. Okay, if you really want to prove this, this will be very similar to how we did that in the homework problem. But you can intuitively, immediately have a feeling of why this is true. Why? Because we can use both the commutative law and the associative law, and together with the help with all kinds of parentheses, which will force you to follow a certain particular operation order. With those tools, you can imagine for any collection of integers, adding them in whatever order you want, you have the same result. But integers are not necessarily positive. They could be negative as well. Okay, this is very important. This theorem is very easy to state, but only being stated in an abstract fashion. So you have to truly understand what it really entails. Now, we will not prove this theorem, but you can use it at your pleasure. Now we will do something really interesting. We'll learn a new concept called the absolute value. We have a weird symbol here. We put an integer a between two vertical bars. And this is a notation for the so-called absolute value of an integer. Actually, if we, in the future, when we further expand our numbers, we will expand our integers to rational numbers, then to real numbers. This absolute value operation is exactly the same. However, if we go even further, move from real numbers to complex numbers, the meaning of this symbol will be different. Okay? So, why? Because we'll see how we will actually define this absolute value. Okay? But before that, let's observe a simple fact. A plus the negation of A, or negative A, equals to, by commutative law, we can swap the order. So both must be the same. But what is the result? The result is 0. Isn't that obvious? Well, it is. And this can be easily proven, right? Because the very definition is that negation of A, doesn't matter A is positive or negative, the negation of A is just a reflected point of A about 0. So the two are equidistant. So starting from 0, you get A and negation of A. So you walk toward both directions about same steps, and they cancel out each other. So you are not doing anything. You are back to the origin. So that's what this means. So in more higher math, abstract math, this is also called the additive reverse, but we don't have to worry about those things. So it's very easy to understand this A plus negation of A, 5 plus negative 5. Remember, negative 5 just a negation of 5. So equals to negative 5 plus 5 equal to 0. So it doesn't matter. As long as you are adding the negation of yourself, you're back to 0. And that negation of self is called the additive inverse. But what is the absolute value of A? Well, the absolute value of A is defined like this. The absolute value A, written as this weird one, we have a integer A. We write its absolute value by putting two vertical bars surrounding this A. So this is the absolute value function, actually. Well, we don't have to worry about that term. Just think about this as an operation. You put a number in, it has a value out. And what you can put into, it's not really limited at this point. You can put anything, 0, a positive integer or negative integer. That's all we have learned so far anyway. And later, if it's a fraction, it's still the same thing. You can put any fraction or rational numbers or even any real numbers. Any number from the number line can be put into this absolute value operator. But if you have number that is not on this number line, for example, the complex number, the meaning of this is kind of different, but essentially very similar for our definition. And what is our definition? The absolute value A is the distance between this integer. We emphasize right for now because every number we have learned so far is an integer. Between this integer and the orange 0 on the number line. That is just nothing, right? It's just the distance. So if you're on the right-hand side of 0, it's the distance between your point and 0. The same thing if you're on the left-hand side. And it's a distance, so it's always positive. We don't have a negative distance unless we define that. But here we define distance, of course, as you would understand it, as an English matter, it's something that is positive. It's really the distance. But because it's always positive, when we say we have a number, we have 2 points on a line, the distance between 2 points is such a positive integer. So this has no direction. You can look this from this point to this point. This is the distance, or you can look from this point to right. This is the distance. So it's directionless. Okay? That's the distance. That's the definition. And without any surprise, if you have a number and you also have the negation of itself, the negated version of this number, both would have the same absolute value, right? Because what is negation? You reflect it on the other side of the number line. But exactly because it's reflected, the 2 points are symmetrical about 0, so they must have the same distance to 0. It's just one from the right, one from the left, right? Which one is from the right, or which one is from the left? So it's very important when you just learn negative integers, you may have a habit to, whenever you see a symbol A, we are using symbolic notation. This is some precursor to algebra true algebra that we'll learn next year. But for now, we are just using symbolic notation to get you comfortable with those letters rather than numbers. But it's very common for young students, whenever you see A, you subconsciously assume A is positive. That's not necessarily true at all. Now we should be equally comfortable with a number that is either positive or negative. So A could be negative in the first place. So what is the absolute of A if A is positive? If A is a positive integer, then the absolute value of A is just A itself, because A is positive, right? Okay, what if A is negative in the first place? Say, what is negative 5's absolute value? Of course we know it's 5, but what is 5? 5 is just the negation of negative 5. In other words, 5 is the negation of 5. We know that. We already know that. The negation of a number go back to itself. So, negative 5's absolute value is positive. It's the negation of negative 5. So, we have the next thing. If what is inside the absolute value operator is negative, A is negative. If A is negative, then its absolute value is negation of A. It's negative A. You have, because you are already negative and you need the positive as the absolute value, so the absolute value is just negation of yourself. Alright? So it's very important when you work with absolute value functions. We'll know what that means. Essentially, if you want to break out or just remove this absolute value operator surrounding A, you have to do a casework discussion. What if A is greater than 0? In that case, the absolute value of A is just A. You can remove the absolute operator. What if A is smaller than 0? Then this becomes negative A. So, you can remove the operator surrounding A, but you always need to discuss those two opposite cases. For those smart kids, you will see, maybe we forgot one corner case, and that is, what if A is 0 itself? Well, what is the distance between a point and itself? The same point. That must be 0, right? That's a no-brainer. So therefore, 0 absolute value is 0. If A equals 0, then the absolute value of A, just absolute value of 0, of course is 0. So essentially, you are discussing 3 different cases. But because this case is trivial, we usually combine this case to one of those the other cases. And most commonly, we put it here. If A is greater than or equal to 0, the absolute value of A is still A, because this case, the second case, actually merged into the first case. It can also merge with the other third case, but that's not usually we do. So usually we discuss, when we remove the absolute value operator on A, we discuss those 2 cases. First, if A is greater than or equal to 0, we can remove the absolute operator directly. It's just A itself. On the other hand, if A is smaller than 0, that's the second case. Then when we remove the absolute value operator, we have to add the negation operator upon A. So either A or negation of A for this absolute value. Okay? So now, with this understanding, we want to really discuss the general addition and subtraction arithmetic of integers. Any integers. So, we first have a theorem. And this is something that may come as a surprise. It's actually not that straightforward to prove this theorem. Alright? But with the help of number line, we can sketch the proof quite intuitively and easily. It's just writing down the full detailed proof. It's actually very long and tedious because we need to do a lot of quote-unquote casework. So, what does this theorem say? Well, if you have two integers, any integer, m and n, the negation of the sum, m plus m, remember m could be negative, n could be negative, or one of them could be negative, or both. The negation of the sum is the sum of the negation. Okay, so how do we prove this one? Well, because so far we have very limited result about the operation of addition and subtraction for integers. Remember what we did last time? We did develop some theorem, didn't we, last time? And that is this one, right? So for any integer m, when you add the negation of an integer, the result is the same as subtract that integer. Okay? And when we subtract the negation of the integer, the result is the same as adding that number itself. Those are the only two theorems that we have proven. So how do we prove this new one currently? If you have two integers and we don't know their signs, it could be one of them is a negative sign and we don't know which one is bigger. So the negation of m plus n is the sum of the negated version of both. So negation of m plus n, how do we prove it? Well, the general proof can be very tedious, but it's just that we can intuitively understand why this is true, right? So we first want to do m plus n. Whatever those numbers are, could be both positive, both negative, one negative and positive. If we, before anything, we do a mimic or imaginary parallel operation, we have another operation m prime plus m prime, just at any step, when we, because how to evaluate this, it's really just counting upward, counting downward, depending on the sign of m plus n, right? As we said, there are actually four combinations: positive, 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 negative, negative, positive, or negative, negative. But we don't care. We just say whenever you are doing this, at the same time, I'm doing the shadow operation. And what is the shadow operation? We do the negation of m plus the negation of n. What does that mean? Meaning that whatever first two numbers, let's just say we have here and here, m plus n, we are doing the shadowed mirrored operation for m here. We take its mirror image here. So this is m and this is n. So we take the mirror point of m. So this is actually the negation of m, or negative m, right here, right? Also take the mirror image of n, so we get this point This is negative n. So whatever result you have here, just think about what do we have here. Because we're just doing the mirrored operation, whatever result you have, my result must be a mirrored version of your result, right? You're doing on that side, I'm doing on this side. Everything has been reflected. So that means that this one is a reflected version of this one. If we further put a parenthesis here, and this, of course, this is trivial, we put a parenthesis there, whatever result you have is a mirrored result. Okay? But that means that after we do this, if we do the result back, this should be back to that one. So therefore, equals to, okay. Of course, this is just an intuitive argument. It helps us to understand how we can write proof. To write the actual proof for this case without any other tools available, you have to do a tedious casework, okay? And to show that, you know, when m plus n both negative are both positive, you get something, take the negation of that, it just reflected, you get this, all right? And when one is positive, one is negative, you have to actually compare which one has larger absolute value. What do we mean by that? So let's just say m is 8. N is negative 5. When we add 8 to negative 5, how do we evaluate this? Well, we know you first from 0 go up to 8, then you go back 5, so it gives you 3. But we will discuss that. But what if this is not 8, it's 17? A plus negative 17? Well, because 17, the absolute value of negative 17 is actually not larger than 8, which is the absolute value of 8 itself, this will give you a net negative result because this is the absolute value, the distance between this negative 17 and 0 is longer than the distance between 0 and 8. So when you add such a large, actually small, but in terms of more just far away point on the left hand side of 0, you bring the total down. The net or the total is actually negative number. A plus negative 17 equals to negative 9. So when you do the discussion of m plus n, take the negation, if you really want, you not only need to discuss the sign of both m and n, you also need to discuss the absolute value of those numbers. That makes the discussion kind of messy, but it's very straightforward to do that. So in order to rigorously prove this theorem, a very simple but tedious proof is that you just discuss the sign of m and n, then discuss the absolute value of rows when one is negative, one is positive, then do the flipping, meaning reflecting, then you show that it's actually equal to this value. But we just gave a very intuitive, very reasonable one, show that if we have a shadowed mirrored operation, this result must be a mirror version of the first result. Therefore, you can add a negation on the first result to get back to yourself. Okay, so we will not write down the detailed proof, but now we just intuitively show why this is true. Okay, remember here, again, don't assume m and n are positive. It doesn't matter. M could be negative, n could be negative, both could be negative. And what do you have when you have a negation of m? If m is negative, that's just positive, right? You have negation. So if m is negative, then negation of m, what's inside this first parenthesis on the right hand side, will become a positive. Okay, so we just have this theorem down. The negation of the sum is the sum of the negations. Remember here we have both m and n will be negated. All right. For those of you who are really keen on concepts like this, you may ask, what if we don't have addition inside the parentheses? What if we have subtraction? So what is the negation of m minus n? In other words, for those smart you, we already wrote it down, which is all good. But what if we have, I don't like a green for this one, I will choose blue. What is this? What is this? What do you think? Well, as it turned out, this is just m minus m. If you look at m minus m, it's actually we apply negation on m and apply negation on negative n, right? Because this looks negative, but remember this is not a negative n. This is subtracting n. But wait a second. Last time we already proved m minus n equals to m plus negative n, right? We proved this last time. Because last time what we wrote is m plus negative n equal to m minus n. But we are just reading from the right to the left this time. So because this is the same thing as this, we just put the right hand side now onto the left hand side. That won't change the nature of the equality relationship. The two are still equal. And by the way, this is called reflective. Okay? So A equals B means B equals to A. Okay? So now we have this. So how do we know this is true? We just pretend this guy is this guy, right? It's a little bit artificial, but this is perfectly fine because we just did this last time. And this is the beauty of algebra. Now, although we seemingly have subtraction inside, we don't have subtraction at all. We really have just addition. So we are just adding the negated version of n, but we already said that this is true for any integers. We don't care whether n is negative or positive. We just care it's an integer. Reflected or negated version of integers is still integer regardless where you began with. So we can apply this result, which is general enough, directly to this version, right? We don't know, we don't have subtraction, we have addition. It's just adding the negated version of the n here. So we can just use the result or theorem we established here in red to this expression. So we will just look at this one as a whole. Okay, the theorem we just proven already told us that you're adding two numbers up, then you take negation. Negation of the sum is sum of negation. So this is truly taking negation on the first one, that's negative m, plus sum of negation, right? Now we have to take the negation of the negative m, not just m. But we know negative or negation of a number go back to itself. So this is just negative m plus n. Okay, this is a lot more similar to this, but it seems still a little bit off. And what can we do further or making further progress? Well, remember, we can use commutative law. Now we put this as m plus negative m, right? This is nothing but commutative law. Now finally, we put n in the first place, m in the second place, and that's similar to this. And what do we need to connect or to make the final push? That's once again this result right here. We proved it last time. Once again, this is just a result that we have already developed. So from m plus negative m, this is just m minus n. This is just a result we proved last time, remember? If you don't need a reminder, it's right there. Last time, m plus negative n or plus negation of n, just m minus n. Isn't that interesting? That's exactly what we have here. So, don't think this is trivial, okay? Because to establish this is indeed true, the negation of m minus n equals to m minus m needs to be proven. You cannot just think, I believe this is right. Or my teacher already taught me this is right. This is the formula I need to use. I just memorized this. But it's super important to understand why this is true. You are not a robot. You are not programmed just to memorize things. You will never be better than the computer at doing that. You are a clever kid. You truly want to know and understand and then memorize why this is true, why it works. And you can see that in order to remove the question mark here, we actually took multiple steps, and each step is needed. So we first convert this m minus n into a form m plus negative n. So now you should understand subtraction is really just another version of addition. Because you can always subtract something and convert it into adding something, adding the negation. So as long as your arithmetic is good for general integer operations, you are not required to limit yourself to some positive integers. We can do this fairly freely. So we convert this into m plus negative m. Now at this step we can use what we just had here. We just proved, remember, that's why we emphasize, cannot be overemphasized, that m and n are integers. They could be negative integers. So, and applying that directly, we get this one. But for negation of n, it's just negation, just n itself. And then we, from here to here, we use commutative law to swap the two. And finally, we use last time's result one more time to get this as m minus m. Therefore, here, after developing this first theorem, we have a corollary. When you have m minus n, we take a negation of that. It's same as if the second integer goes first, subtracting the first integer. So that's how we know something like this happened. But is this the same thing as say we want to evaluate 5 minus 3 minus 17? Nope. Why this is not the same? Can we use this, say this is 5 minus 3 plus 17, or even better, this is plus this. Can we do that? Yes and no. We cannot jump here to here directly, but we can prove this is true. In other words, we should establish a theorem first. And then with that theorem, we will be able to show when we want to evaluate this, we get something like this. Otherwise, every time you go from there to here, you need to make some argument. Okay? And instead of making an argument every time, we want to generalize all those case-by-case argument into a general theorem, so that whenever we have something like this, we can use a theorem directly for all cases. So that's why we have the next theorem. This is continuing. Okay, if we have three integers, L, M, N, L subtracting M plus N is the same thing as L minus M minus N. Why we are doing that? Why this is true? How can we prove this? Well, I could leave this as a homework to you, but that's just prove it and give you some more interesting homework. By the way, I haven't given you any homework for a while, but that's because I have some just a personal workload issue, but I promise I will give you something soon. Okay, so L minus M plus N. What is this? Well, this is L subtracting a number, right? But we know this can be written as L plus. Remember subtracting number? Now we established that subtracting number is just adding the negation of that number. So it's just this one, right? We're subtracting whatever came out of this parenthesis. This is the same as adding the negation of whatever that comes out of the parenthesis. This is what we proved last time, right? What we proved today is that at this point, you can take out of rows, put them into negation of M plus negation of N. That's what we did today, right? Negation of sum is the sum of the negations. Now you can see that, what can we do? We can use associative property to write this as L plus negative M, then plus negative M, meaning that now we will do the first two. We don't need the parentheses because this is just the default order. But what is important to understand at this step, this is just what? Associative law. Now we use the result from last time again. We can convert what inside this parenthesis that's made it explicit. This will be L minus M, right? Because you add in the negation of M, that's the same as L minus M. Now we are adding a negation of M. But we know at this point, once again, we will use the same from last time. This will be LM, subtract M, subtracting. Now we are looking at this portion of our expression. We're adding the negation of the number, and that is the same as subtracting this number. Look, what do we have now? We have exactly what we want. This is nothing but this, because the parenthesis also is optional, or I could put a parenthesis between the first two, but just chose not to do that. So this is exactly how you prove this theorem. It takes multiple steps, but each step is quite easy. Okay? Don't assume just because those are easy together you think this is obvious. Okay. If I ask you at this point to prove this, can you do it? Can you do it? Well, you don't have to, because we already said that in grade 5, we are not asking you to do any proof. However, we want you to observe what the proof is about. It's about a rigorous reasoning, starting from a statement through a chain of reasoning, arriving at another statement which you show that's true, must be true mathematically. So that's what we just did. Why this 1.26 equation is true? We went through a process like this. Okay? So one step at a time, but each step must be rigorously reasoned. Okay? This is the steps it takes to prove this one. Okay? So you can see it's not that trivial at all, because each step we need to explain why this is true. You can never ever say, I think this is true. This is obviously true. Yeah, sometimes you can say, I take that back, you can say obviously true, but that must be truly obvious. You cannot just say, I cannot do this, so therefore I chose to say this is obvious. No, that doesn't work. It's obvious only when absolutely no doubt this is logically clear, this must be true. So that at that situation, you can say this is obvious. Obviously, you get that. Otherwise, you will be cheating. So we did not do that. Every step of the way, we justify why we are doing that. Okay, so now with this theorem, you will ask exactly the same question you asked earlier. What if we don't have plus inside that parenthesis? We have a subtraction inside that parenthesis. In other words, what is L minus M minus N? What is that? Well, we will do exactly the same as last time. So this will have a corollary. L subtracting another subtraction inside the parenthesis will give you L subtracting the first operand inside that parenthesis, which is M, but plus N. Intuitively, you think that the negative give you positive, but remember, this is not negative. Neither is the second one. They're both subtractions. So that's a misnomer. When you say negative, you are talking about the negation. We are talking about subtraction here. Subtraction is a different operator from the negation operator. So just because you have negative n equals to n, you cannot just say here, that's why we can write this as L minus M plus N. But we can certainly prove this. How? Did anybody notice that we didn't say this is a theorem, we only said this is a corollary? What is a corollary? Corollary is also a theorem, but this theorem is directly established upon another theorem, and the connection is very short. It must be true because we already proven theorem 1.14.3, and this 1.14.4 must be a direct result that should be easily available if we have established the former, and that's exactly the case. And we will show why that's exactly the case. We just proven this, right? think this is a little bit too thin, so we just proven this, right? Now we want to prove plus n. We don't know. Let's give it a try. How do we prove this? Well, remember last time when we don't have a subtraction operator 1, we only have a negation operator, we pretend this is a it's inside the parentheses, it's not subtraction but addition. So this is nothing but m plus negation of n, right? This is our result from the last lecture. Subtraction is really just addition but adding the negation. Okay? Now we can use this. Because what is inside the parentheses now is addition, not a subtraction. And that's what we have. Remember, we don't assume n or m to be anything positive or negative. It can be anything. As long as n is an integer and the negative or negation of n is an integer. So we just view this one as the n in this result. Therefore, we can directly use this result and we will learn this. It's on the right hand side. It's L minus m and minus a negative n. Now we know what happened to this one. This one, because if we group the first one first, this is just nothing but plus n. Remember? That's it, what we have last time again, right? We also, if you forget, subtracting the negation of n is adding that number right here. 1.23, equation 1.23. Okay? So m subtracting the negation of n, just m plus n. Because of that, here we have this, subtract negative n. But what is this? This is, of course, what we just wanted. And this is the corollary. So you can see that the reason we call this is corollary rather than the theorem is because we can actually use the theorem in a very convenient way. Make this theorem actually trivial. It's just a direct result from the earlier theorem. So therefore, now we have established two very important theorems that confuse a lot of young students when they do arithmetic involving parentheses and negative integers. But here, remember, when we say negative, we only mean they look like div. N could be actually positive. So it's n. So let's do some simple examples. Okay, what is 12 minus 25? What is 12 minus x5? Well, 12 minus n5, you are not used to this. I don't know how we can get 12 to 25. 25 is smaller than 12. But based on the theorem we can use, this is just the negative or negated version of 25 minus 12, right? That's the very first one we proved earlier today. If you need a reminder, yeah. So, therefore, this is nothing but negative 13 because we do know how to evaluate 12 of 25 minus 12. That's what happened when you think about 12 minus 25. You're subtracting a bigger positive integer from a small positive integer. In your mind, you are actually doing 25 minus 12, not 12 minus 25. You are doing the negation first. But you do know after getting the result, you need to get the negation back to cancel out the first negation. So negation of negation, it's just itself. So that's how actually you get this negative 13. It's because of this result. All right? So now, next what is negative 23 minus 45? Well, according to our theorem, this is nothing but 23. No, sorry, 23 minus 45. This is nothing but we are actually doing addition, right? We know how to do addition. We don't know how to do negative minus negative, but we do know how to do addition. But according to our theorem, we can put that all the two symbols. Remember, those two symbols are not the same. The first one is a negation on 23. The second one is subtraction. But regardless, we can write this as this. So this is negative 68 because we know how to do addition. Okay? So let's do some more complicated. What is this? 32 subtracting inside the parentheses 21. Yeah, we can do that. We can use what we just learned, perform a 72 minus 21 first. That's just 51, but remember that's negative 51. So this could be 32 minus a negative 51. And this will give you 32 plus 51, that is 83. Or perhaps someone prefer to do that. I don't want to evaluate a negative subtraction inside. I just want to get rid of the parentheses first. So you can do that. Remember, we just proved the theorem, right? We just proved this corner. We can remove this. That's 1.27. So if that's the case, 1.7 tells us that we can do 32 subtracting 21 first, then add this 72. That makes this a little bit easier because now we are in familiar territory. 32 minus 21, we know that is 11 plus 72, that's 83. So it doesn't matter which way you take. You can evaluate what's inside the parentheses first, then get the second operation, or you can get rid of parentheses first, but just be very careful how you deal with the negative side when you work with parentheses. And then there's a subtraction operator right before the parentheses. You need to really understand today's theorem, okay? Let's take one more example. What is this? Okay, 53 minus inside the parentheses, negative 18, subtracting 78. Again, you can do the same thing. So this will become 53 minus negative 18, then plus whatever that's 7 is 78. So let's put 78 there. And you can further reevaluate this as 53 plus 18 plus 78. And you know how to do all that. So the point is that with today's theorem, any complicated subtraction, addition, arithmetic with negative integers, with parentheses, no matter how many, you know how to handle them. Just repeatedly applying what we have. For example, like this one, you can evaluate what's inside the parentheses first, or you can get rid of it. This is nothing but just adding 25, subtracting 74, right? But what is negative or subtracting? Remember, I should be very careful about my wording. In the last expression here, the first one is a subtraction. The second is also subtraction, but inside the parentheses. Therefore, this is 82 minus 25. Then after you evaluate this first one, then plus 74. Okay? So that's it for today. It's very important to understand when perhaps your teacher already, depending on which grade you are, if you are already in the 7th or even sometimes some students in advanced in the school, you have already learned how to do those things, but your teacher taught you the rules and you trust your teacher, right? You should, right? You trust your teacher and believe those rules are true. You just follow the rules to evaluate. what we did to explain those rules in the format of some rigorously proven theorems. That's the difference. I will see you next week. Thank you. Bye bye.